Hi guys, welcome back. Today we'll be doing electric circuits. Please subscribe and like and share. Okay. Here we are given a simple circuit. We're given a battery, a light bulb, and a switch. Okay, physical sciences, grade 12, electric circuits. So focus of the lesson, we're going to look at introduction. We'll also look at factors affecting resistance. We'll look at Ohm's law. We'll look at series and parallel connections. We'll look at potential difference in the EMF, electromotive force. And then we'll look at the internal resistance. We'll look at the electric energy. And lastly, we'll look at the power. Okay, introduction. This is the study of electric circuits. Is essential to understanding the technology that uses electricity in the real world. In grade 10 and 11, electrical circuit problems were simplified by ignoring the internal resistance of the battery, the small r. But in grade 12, we will learn to solve problems in which the battery has internal resistance. We need a source of energy or a battery or a cell for a current to flow, to push those charges in a conductor. And potential difference is the work done per coulomb of charge to move the charge between 2 points in a circuit, and then it's measured in volts, the SI unit, and which is measured by using an instrument which is called voltmeter. And then we know that V is equal to work done divided by charge. Electric current is the amount of charge passing a point per unit time, right? In other words, we're dividing charge by time. And ampere is the SI unit, which is measured by instrument called ammeter. So this is I is equal to Q over T. Now we've got resistance, which is a measure of how much conductor opposes the flow of charge through it. In other words, it resists, the flow of charge. And then it's measured in ohms, which is the SI unit. Now, let's look at the factors, affecting resistance. Number one, the length of the material. The longer material have got greater resistance. In other words, here you've got a small material which has got small resistance, and then here you've got 2L, the length, the larger material which has got larger resistance. And then another thing, you've got cross-sectional area of a material. The larger areas offer the less resistance. Here you've got small cross-sectional area, which means you've got larger resistance, and then here you've got larger cross-sectional area, which means you've got small resistance. And now the other thing is temperature of the material. Higher temperature usually result in higher resistance. You'll see this using an Ohm's law. The kind of material, the type of material, iron has got more electrical resistance than a copper conductor. Now let's look at the Ohm's law. It states that potential difference across the conductor is directly proportional to the current in the conductor at a provided or at a constant temperature. So we know that V is directly proportional to the current, voltage, potential difference is directly proportional to the current, right? For us to change this proportionality constant, we we must put a constant here, right? We must put a constant R. Okay, so now in the diagram, you've got here on our y-axis, you've got your potential difference, and then here on the x-axis, you've got current, meaning that now when your potential difference increases, also the current increases. And then in other words, we also know that the slope, of this graph is the resistance. In other words, this resistance is going to be constant throughout the line, whether you calculate it from here or here, is going to be the same, and then R, so which means the resistance is being given by changing V, the y-axis, over changing X, which is the current. And now R is equal to V over I. So now we've got this rule, we did this. So V is equal to I multiplied by R, which is this one. And then we can just say V is equal to I multiplied by R, and then I, it will be V over R. And then now the Ohm's law will be this R is equal to V over I from the diagram. Okay, now let's look at the resistors in series. You've got resistor R1 here, R2, and R3 here, right? So now the current is passing through here. So here in resistors in series, we know that the current is the same throughout. I1 is equal to I2 is equal to I3, right? So, but for a voltage is different, right? That's why we call it a potential dividers. Resistors in series are potential dividers. In other words, the potential will divide, for instance, here, the 2 ohm will have 2 volt, and then the 3 ohm will have 3 volt, and then the 5 ohm will have 5 volt. And then the total voltage here, you just add this 2 plus 3 plus 5, just using this formula, V1 plus V2 plus V3, which will give you the total of 10 volts here, okay? The total resistance in a circuit, increases when more resistors are added in series. This is very important. When you have got a lot of resistors in series, when you add them, it means that the total resistance, it will increase. And then now the current through all resistors in series is the same. I've said that the current doesn't matter whether you measure it here or here or here, it's just the same. And then now, if one of the resistor burns out, the circuit is broken, or no current, will flow. If this one is burned out, it means that now the current cannot go to 3 and 5, right? The circuit is broken. Now, let's look at the resistors in parallel. Here, your current is supposed here, the current is coming from A. So when current gets here at the junction here, so it's going to split. The other current will go down here at I1, and then the other current will go to the other side. So now we're saying that resistors in parallel, they are current, dividers. In other words, current will divide, amongst the resistors. So now the IT here, it means that I1 is going to be I1 plus I2 plus I3. But here, the potential difference in each and every resistor here is the same, right? Potential difference is the same. And then now, for the resistance, you say 1 over Rp, which is equal to 1 over R1 plus 1 over R2 plus 1 over 3. You know this, right? So the total resistance, this is also important in a circuit, decreases when more resistors are added in parallel, because that you get the ratio. That's why it's sort of decreasing when you've got a lot of resistors in parallel, the total resistance, it will decrease, unlike in series circuit. So now the total current in a circuit increases when more resistors are added in parallel. Now also the total current is the total current in a circuit increases when more resistors are added in parallel, right? The total current will increase because it's going to be divided here amongst, but the total now at the end here is going to be the sum of all the currents, so it's going to increase. And if one resistor burns out, the current still flows through the other resistor. Also you can think about your home, those light bulb. I can ask you a question: are they connected in series or parallel? You just have to figure out using these, statements. Because now, if maybe the light bulb, in the kitchen is burnt out, does it affect the other light bulb in a bedroom? Just have to think about that. Okay, now, in other case, given two resistors in parallel, normally we say 1 over R equivalent is equal to 1 over R1 plus R2. All this, it can also be written as, if you don't want to use this formula, you can come and use this formula. R equivalent is equal to R1 multiplied by R2 divided by R1 plus R2. We can use this formula here. You can just get this formula. We got this formula from this equation, by just manipulating here. So now let's look at the potential difference in the electromotive force. Here, what they're saying that the EMF is the maximum potential difference between the electrodes, or coming from the battery, when no current is flowing, when no current is drawn from the cell or battery, right? In other words, when the switch, or when the circuit is open, right? When the circuit is open, now you have got your EMF here, right? And then now this EMF is also independent of the resistance of the circuit. It is greater than the potential difference, okay, between any 2 points in the circuit. In other words, this EMF is greater than this potential difference between this point here, or rather between this point here, right? So EMF is bigger than this, right? So now let's look at the potential difference, the PD. The potential difference is the difference, okay, of potentials between the 2 points in a closed circuit. So here we talk about potential difference when the circuit is closed, in other words, when the switch is closed. And then now it is proportional to the resistance between the given points, okay? It is measured between any 2 points of the circuit. However, the PD, the potential difference, is greater than EMF when the cell is being charged. When you're charging your cell phone, when you're charging, whatever you're charging, just know that the potential difference is greater. That's the only case when the potential difference is greater than the EMF. Let's look at the internal resistance. That the internal resistance, we normally find it inside the battery or inside the cell here. So now this is internal resistance. It's represented by the small letter R, right? And here you've got a cell whereby you also get your EMF, right? And then here I said Vx. So this Vx, some they call it V terminal, right? That's the voltage which is going to be used by this resistor and other resistor if they're there, This is the Vx. That's why it's voltage which is going to be used externally. So when the switch is open, the voltmeter reads the EMF. When this switch here is open, this voltmeter is going to read the EMF. Yeah, as a matter of fact, because now there will be no item here which is using the, the current or the voltage here, because the switch is open, When the switch is closed, but immediately when you close the switch, the voltmeter reads the PD of the external circuit. When you close here, the voltmeter will read the PD of the external circuit. Internal resistance is found inside the battery or cell. I've said that, which is the small amount of energy that is used up inside the battery or cell, or lost inside the battery or cell. Now, the volts used inside the cell are referred as a lost volts. Okay, now let's also look at the internal resistance. So now suppose here you have got the EMF here of 3 volt, and you don't have a internal resistance, right? So it means that if you don't have internal resistance, or when your circuit, when the switch is open, it means that now the terminal voltage of Vx is going to be equal to the EMF here. Without the internal resistance, EMF is equal to Vx. But immediately when you have got the internal resistance inside the battery, it means that now your EMF here is greater than your Vx. Here we're saying that the terminal voltage of V external, or external voltage is equal to 2.4 volts, is less than 3 volts. Now let's look at the EMF of the cell. Is the electrical potential difference across the terminals poles or poles of a cell with no current flows, when the current is not flowing. In other words, when the switch is open. It's also measured in volts. We know that R is equal to V over I from the Ohm's law. So we can rearrange this and get V is equal to IR. So it means that the EMF now is equal to V terminal or V external plus V internal, right? Voltage inside the battery or voltage lost. Now, also know that the V, we're given that V is equal to IR. So EMF is equal to V external is equal to IR, and then V internal is equal to I multiplied by small r, It makes sense? Now the I is common, we take out the common factor of I, and then we get EMF is equal to I into R. In other words, we say this is R external, it still makes sense, plus R internal, okay, the small letter. So now electric energy. When current flows or charges move through a resistor, electric energy is transferred from the moving charges to the particles in the resistor. So the temperature of the resistor increases, the kinetic energy of the particle increases. This is true. And also it's measured in joule. We know that work done is equal to the energy transferred. That's true. Okay, now work done is equal to energy transferred. We know that E is equal to VQ. So it means that W is equal to VQ. We also know that Q is equal to IT, which will give us V is equal to VIT, and we also know that V is equal to IR, right? So now we just come and substitute this V by IR to be I squared T. So you've got I squared RT, and then also we just come and substitute this I by V over R, by V over R. So now you have V squared TR. You're going to get V squared TR. And then we also know that work is measured in joule, volt is measured in volts, voltage is measured in volts, and then current is measured in ampere, and resistance is measured in ohms, and time is measured in second. So now let's look at the power. Power is the rate at which the work done or energy is transferred. The rate means that we're dividing work here by time. Okay, so now power is equal to work divided by time. You remember the very same definition we talked about when we were doing work, energy, and power is still applying here. Similarly, P is equal to voltage multiplied by current. And then we also know that V is equal to IR. So where there's V, you just substitute IR. So you'll have got, you're going to have I squared R here. And then also now that we can substitute I is equal to V over R. So where there's I, you just put V over R, you've got V squared R. You've got V squared R here. So also know that power is measured in watts, work is measured in joule, and voltage is measured in volts, current in ampere, resistance in ohms, and time in seconds. Okay, now let's look at the example number 1. So I will do this example with you guys. I'll try to be fast. Sometimes I struggle with my pen here, but I will try to be fast. Okay, now they're saying that calculate. So now you are given the battery of the EMF of 20 volts, and also you are given internal resistance of 1 ohm is connected to 3 resistors as shown below. So now you have got this resistor and this are in parallel. So now they're saying that calculate the current in the 8 ohm resistor current here, right? So I think the best way to start this question, you can come and see it has got 6 months. You can start here. You can see EMF is equals to I into, I'll try to be fast, R plus small r, right? So now, what is the EMF you're given? And then we're looking for the current, all right? So that current here, the current which is coming here, this is positive. Current will move from positive, current will move this side, right? Okay, now it means that we just have to calculate the R tot. So now we can start here by calculating the R. You can come and say RP, I'll just say this is R parallel, right? RP, which is equals to R1 multiplied by R2 all over by R1 plus, yes, plus R2, right? So now when we try to substitute here, what is R1? R1 is 5. You're going to get 5 multiplied by 10. Right, that's 50. All over by 5 plus 10, right? So now for your RP, you should get about, we said 3.33, just punch this on the calculator. You should get 3.33 ohms, isn't it? 3.33 ohms. So now you got the current, here. So it means that now you can edit. You can just come and say, I don't want to say R tot, but I'll just come and say R8 plus R8 plus RP, right? R8 plus RP, and this should give us, is it about 8 plus the RP, which is 3.33. Are we together? Okay, now the total of that, I'll just say equals to here. The total of that should be 8 plus 3 is 11.33. You should get 11.33. 11.33 ohms. Okay, now guys, you have got your R here. So that's R tot. So now you can come and substitute, you can just come and say we are given 20. So it's going to be 20 is equals to 20 is equals to I. Are we together? 20 is equals to I into 11.33 plus the internal resistance, right? Plus the internal resistance, which is 1, right? So now this one, is equivalent to, this is equivalent to 20 is equals to I into, is it 12? 11.33 is 12, yes. It's 12.33. All right, are you following? So now you just come and divide both sides by, so now your I will end up being, so you will end up having your I is equals to, I'll just show all the steps, because some people, they cannot follow, to be 20 all over by 12.33, which is equals to about 20 divided by 12.33. You should get about 1.62. You should get 1.62 amps. Right? So now this is I. You should say this is I 8. Okay. So now we got the first one. So now which is this one. So now they're saying that calculate the potential difference, across the 5 ohm. So this is here. So now one thing we know that about the voltage, the potential difference, in a parallel connection, we know that the voltage, the potential difference is the same. So we can just come here and try to solve this side. Number 2, it will be, so already now we've got this RP here, right? So potential difference is given by V. So how about I say V of 5, right, is equals to, V of 10, because we're just looking for the potential difference here of 5, and which is equals to V of P, right? And then basically we know that V is equals to IR, right? We know that V is equals to IR. So now it means that the V, it will be I, it will be the total current multiplied by RP. I can just say RP here, right? Which is equals to the total current, it was 1.62 multiplied by RP, which is 3.33. 3.33, right? And then we're looking for the voltage here. So when you times that, you should get about is it 5.40 volts? You should get about 5. Sorry about that. You should get 5.40 volts, right? Okay. So now, given that, to go to number 3, it says that calculate the power. We know that power is equals to, this is number 3, power is equals to VI. So for the power delivered by the battery, the battery is here. So it means that you should use EMF, right? It means that you should use the EMF. So in other words, it will be 20. It will be 20 multiplied by the current, which is the total current of what? 1.62. Okay. 1.62, right? And then we said that the power is measured in watts. So you should get 32.4. You should get 32.4 watts, right? Okay, we're done with this example number 1. Just got 13 marks. Okay, this was the previous question paper. Let me erase this all. Because we're going to have another problem that we have to look at together. Okay. Now okay, we're going to look at another problem here. It's not challenging. I also took it from the past papers. Okay. This is the problem. You said that A battery with an internal resistance of 1 ohm and a known EMF is connected in a circuit as shown, a high resistance, a high resistance voltmeter V, it's this one. It's connected across the battery. It's connected across the battery, and then we've got A1 here and A2 represent the ammeters of negligible resistance. So now you're given this. Okay, now switch. The thing that with switch S closed, okay, the current passing through the 8 ohm here, the current passing here is 0.5 ohm. So now the thing that states the Ohm's law, we said that Ohm's law, the potential difference across the conductor is directly proportional to the current in the conductor at a constant temperature. Okay, that was number 1. Okay, now they're saying that the current here is 0.5. We've got current of 0.5 here amps. We've got the current at 8. So now the thing that calculate the reading on a ammeter A1, right? The reading on the ammeter A1. So in other words, once we're given the current here, it means that we can get the voltage there, right? We can get the voltage there, and then that voltage will be also equal to the voltage here at the 16, right? In other words, we can add those two currents and get the A1. So we can do it. Just say V. This is number 2. Let's say V of what? V of 8 ohm. It's equals to I R of what? R of 8 ohm. No, which is equals to. So now the current, they were told that is 0.5. We're told that the current there is 0.5. Okay, multiply by R8. Our R8 is 8. Okay, and then by that by just you can just use the calculator there. You should get about 4 volts. You should get about 4. That's half of 8. Now, in other words, that's half of 8. You should get 4 volts. So now this 4 volts here is also equal. So in other words, the V of what? The V of 16. The V of 16 is also equals to, because they're in parallel, right? And then we said in parallel connection, they've got the same voltage. So the V of 16, it has got 4 volts. So now we are here. We know the voltage. We know the voltage here. We know the voltage here. We know the voltage here. Okay, that we've got another 4 volts. So can we get the current at 16? So now for us to get the current, we can come and say I I of what? 16. Okay. I of 16 should be equal to V over R. It should be equal to V over R. Right, and then already we know the V of 16, and then we know the R of 16 where it's given. Right, so this by default it should be equals to, this is 16, 4 all over by 16. Okay, all over by 16, and then you should get the I of 16 is what, 4 divided by 16, you know, is it 0.4. Okay, now you get 0.25. You get 0.25 what amps, right? 0.25 amps. So in other words, now we can come and calculate the IT now, the current total, the IT, which will be equals to I of 8 plus I of 16, right? So you should get so here at I8, so they should, this total of this, they should come here and then they should give us I1. So now it will be I of 8, which is 0.5, 0.5 plus what? I of 16, which is 0.25, 0.25, right? And then that by itself, it should give you 0.0 0.75 amps, right? So now we know the current here at I1 is 0.75, right? Okay, now we're done with one. So now we're done with this one. So now let's come here and then doesn't that if R delivers power of 12 volts, where is R here? You are telling that if R delivers the power of 12 here, you are told the power here, that is 12 watts. You're told that is 12 watt. That's it. That now calculate the reading on the ammeter. You know what will be the reading here? What will be the reading here? This is a question mark. What will be the reading here? Okay, now the simplest way to do this, since we here, you know, you get the current. How about we add this resistance and then we add this one also, right? And then we get the voltage there. So that voltage, it will be equal to the voltage here. We can use that principle, Okay. Now we say we'll go back now to the RP formula. Those RP is equal to R1 multiplied by R2. Okay, now RP. So now we're doing this is number 3, right? And this was number 2. So now on number 3, we're starting with the analogy that RP I'm struggling with the pen. RP is equals to R1, which is 8, multiplied by R2 all over by R1 plus R2, right? Let's set to be first. So your R1 is 8 multiplied by 16 all over by 8 plus 16, right? Which is directly equal to, which is equivalent to 5.33 ohm. Here you can get 5.33 ohms, right? So now here, so we can also come and add that one. So we can I just come and say R8 is, to say R20 plus RP, right? Plus RP. It means that also that by itself is equals to 20 plus 5.33 and that should give you, I'll just come and write it here, that should give you 25, right? 25.33 watts ohms, right? Ohms. So now you are given the R tot here in the upper branch. I can just say this is upper branch, and then this is lower branch, right? So now here you are also told that the current, the current here is going to be the same throughout. So you can come and calculate the voltage. Okay, now the voltage on the upper branch, I said this is upper branch. So the voltage on the upper branch, is equals to the voltage. The voltage that I'm talking about is a voltage, from here. I'm talking about this voltage here. I'm talking about that voltage, or V parallel if you want to call it, or V parallel. So it's going to be I R, right? It's going to be I. It's going to be I R, R, or R of 20 plus P, right? So R, we use this one. Sorry about that. So you are going to get what is our I? Our I thought in that upper branch is 0.75 multiplied by 25 point here multiplied by multiplied by 25.33 all together. So you should get about 19 volts here. So it's telling that now the voltage here on the upper branch is 19 volts. Similarly, the voltage here on the lower branch, it will be 19 volts, right? Okay. So now, what can I write? The last question, maybe it will I will try to squeeze it here. Maybe it will fit. Okay. Now, so for us to get the voltage A2, we can just come and see we're given the power, mind you, there. So the power, we know that power is equals to V what? VI, right? And then what is power there? The power is 20. The power is 20. So we got the parallel. So this, mind you, this is also equal to the voltage at V R, for you not to be confused. I just say V. So it will be 20 is equals to, what is the voltage there? It's 19. Okay, it's 19. Multiplied by I. So you just divide both sides by 19. You should get okay. So here it's not 20. I think we made a mistake there. We should get here the it was 12, right? It was 12. The power was 12. I'm confusing it with the first question. So now when you divide both sides, you should get I equals to 0.63. I equals to 0.63 amps, right? So that's the current at I of A2. This is the current which is equal to the current of A2. This is A2, right? So now they're saying that the last question here, they're saying that calculate the reading of the voltmeter. Okay, the reading of this voltmeter here when the switch S is open. So you just open here. So now when the switch S is open, that I said that the circuit, the voltmeter will read the EMF. I said that, it will be equal because now the current will go this direction and then it will come and stuck there, right? Because the circuit is open. So now the voltmeter will read the EMF. Okay, now we can do that one first. Let me erase somewhere. Let me erase. I'll try to erase here. Don't forget the other values we got from here, but I will just erase here anyway. I will erase here only. Yeah, it should fit. Okay. Okay. So now I said the EMF is equals to, I've said this before, right? I say that I'm saying that here when the switch is open, V is equals to, let me just write V is equals to EMF. Reason being that the switch is open. So you know that the EMF is given by I into R plus R. Are we together? So now the kind thing that you have to calculate this V, which is equal to the EMF, which is equal to V, which is equal to the EMF. So now we know R, I think here we know all that. Okay, now to remove the bracket here, it will be IR. Are we together? Multiply by I small r, right? Just to remove the bracket. So now we have got IR is, I said, is V external. I've said that is V external or terminal voltage plus V inside the battery. V inside the battery. I can just say V in, right? I can just say V in. So do we know V external here? We have calculated V external here because it's the same throughout here. So it's going to be 9 volts. It's going to be 19 volts here, right? Plus, so IR, is the total current. Do we know the total current? Yes, the total current is this one plus V into, which is IR, we can just come here and see 0.75. We know that we'll go to 0.75, right? Which is just the sum of 0.5 from here, and then also, oh, okay, now we got 0. Here we got 0. So now the current here is 0.62. The current here is 0.63. So we should add these two currents. So 0.75, allow me to say, plus, that's still a current, plus 0.63 plus 0.63 right? Multiply by internal resistance of what? Of 1. So this all should give you about 20.38, 20.38 volts, right? In other words, that's EMF. That's the EMF. So you are done here. Okay. So now allow me to erase all this. Okay. So your home task, Elena, want to use a 12-volt battery with an internal resistance of 1 ohm, to operate an electrical device. This electrical device uses the electric circuit below to obtain the desired potential difference for the device to function. The resistance of the device is 5 ohm. So this, when the switch S is closed, so the device function at its maximum power. The power here is 5 watt. So now the same explain the meaning of an EMF of 12 volt, calculate the current passes through the electrical devices. Simple. Calculate the resistance of the resistor RX here. You've got your RX here, and then switch S is now open. Will the device still function at maximum power? Explain. So now this is your home task. Work on it. Put on the comments if you've got questions. Don't forget to subscribe, to like, and share. Thank you.